All right. So move semantics. I kind of already started explaining a little bit about the when you have a class or a class type, right? Maybe a struct or maybe a class. And if you have not defined your own, you know, copy constructor or copy assignment operator. Now here's an example, right? This is this is a copy constructor. This is you're passing in another memory block. This class name is called memory block, a block of memory bytes. And you're passing another object and to construct another object as a copy. And so this, as you see the implementation here, actually will use the copy assignment operator. So typically the assignment operator goes together with the copy operator, because we actually just reuse the implementation of one to implement the other. So here, this, if I hover over this assignment operator here, it's going to show this. Now, because now we know, now understand how the operator is overloaded, right? So here we're overloading the assignment operator here, the operator, the equal sign. And this is going to show, okay, it's going to actually invoke this function right below, right here. We have overloaded. And the right-hand side of this is a, this other is a const. It's a constant reference to memory block. So in this case, the compiler, essentially realize, okay, you have this thing defined, and so it's going to use this, what's called copy assignment operator. Copy assignment is making a copy of it, making a copy of this other object. And so now, to make a copy, first of all, you want to make sure that you're not copying yourself, right? So it only works if it's the same object as this object, then you just simply return this object. There's no operation to do. There's a no op. Now, if it's different, in this case, this data is a member variable. It's actually a integer pointer, or actually points an array of integers, and then we also have the size or the length of it. So you want to free that existing resource. Now remember, if this data is a null pointer, this is actually a no op. Like, this deletion operator is not going to do anything. So there's no harm. If it's, you don't need to do a null pointer check here. And so then we just copy the length, and then we also need to allocate. Now remember, the array, previously we introduced about the array type, is a little different. You can't just assign an array to another. That doesn't really work. And so what you do, you have to allocate a new array, and then you perform a member-wise copy. You copy all the elements over, and this is the standard copy algorithm to copy those things over. So this is, we can do this. It's very efficient. So, but again, if you can avoid a copy, then you have to avoid a copy. But then this is what it will do. If you have an array, then you have to copy it. So this is what this will do here. Now, what if in some situations I don't want to copy? There are situations you don't want to copy, and we might see some example, in a bit. And so there's this thing called the move constructor. The move semantics, so that's what move semantics means. It's about these two things here. So again, the assignment operator and the constructor go together. Now this just looks, there's a tiny little difference here compared to the copy constructor, okay? Here we have a const reference to an object, and here we have this double ampersand. The double ampersand represents the R value reference. Okay, so this is a reference also, just like here, this is, this particular format, by the way, is a const reference. Now this reference ampersand typically means a L value reference. Now, when you declare this as a const reference, this also can receive as a function call. This can receive an R value as well. Now, R value, you know, like number 1, 2, right? Like a constant expression that is, you know, it's called a PR value. That's just one example. There's many R values. And the R values, typically what it means is just intuitive thinking. Those are the values that don't have, okay, they either don't have a address in memory, or they have a temporary one that's about to expire. There's, you know, if you are, and I thought I had an example here because anyway, so let's say you are returning a value out of a function, and the value that you return is you're constructing a new object. And that construction of new object here, and then you return that immediately, right? That construction of this new object, then you have an object, you know, with using the constructor right there. That is a temporary object, and because it goes out of scope of the function immediately because it's in the return statement, right? So that is a situation where the move semantics can help. You don't, you know, again, well, although the compiler is going to operate in that particular situation, the compiler probably will optimize to not do a copy, you know, just so that the lifetime of that temporary object is extended into that return value, which will be used in another function, right? And then the lifetime of that object is valid from that point to the end of that function. So the caller function of that one. And so that is really the whole point of a move semantics to just essentially, it's an optimization. It saves time and resources to do unnecessary copies. That's really what the main thing is. Now, so here, this is all value reference. And we're gonna see, here, just let's look at the example, how this is implemented, right? So the all value reference is also a reference. Now, the all value reference can only hold all values, right? And then versus this here, it's a const L value reference, and this actually can take an L value or an R value. And but in this case, we're doing a copy. Now this, you're providing something that's temporary. So if something is temporary, what we can do is we're going to take over that object, and sort of whatever is in that object, I'm gonna basically, we're gonna take it over essentially, in a sense that it'll be now this move, by the way, it's a kind of misnomer. I don't know why they call it move. Move, it's just actually what it does is converting an L value to an R value reference. Now this assignment operator, as I hover over this, this is going to invoke the operator that we overloaded just right below line 73. Right, this shows up the signature right there, or the function header, and that's taking a R value reference as a parameter. Okay, so this move from the standard namespace, what it will do is convert other. Now, here's a funny thing. You're saying, okay, you're saying this parameter is actually taking a R value reference, right? The ampersand, the double ampersand. Now, although it's taking an R value reference, this actually, it gives a reference of an R value. Now, the expression of other, this other expression is actually an L value. Why? Because other has a memory location. It is an L value. This has a name, and this name is allocated in memory. You can access that location. So But this, you know, we need to basically convert this into a all value reference again, so that we can utilize. Now this is reusing this assignment operator here, okay? And so in order to reuse this, because we're implementing a move semantics, we want to move the object. When you're constructing a new object, you want to just remove that temporary object into the object that we're constructing. And so we're just utilizing this assignment operator. So we need to actually pass in an all value reference here so that it will invoke this. Otherwise, if you don't do this, it will be just a copy. It will go back to doing the copy assignment operator, right? So here, what we're doing here is, see, is interesting. We're not doing a copy anymore. And what we're doing, essentially, we're stealing the pointer of data. We're saying we're gonna essentially, take over that pointer, right? This is the head of that memory buffer, right? And so it's a pointer, it's an integer pointer. And so what we'll do is we'll just take that, so this current object's data will point to that same location. But doing that is not going to be sufficient, because when this other, now this other will go out of scope at the end of this function, right? This is a parameter. This other will be out of scope at the end of this function as soon as you return. And when it goes out of scope, it will be, the destructor will be, or if there's has destructor, then it will be invoked. In this case, the destructor of a memory block will be invoked. And the destructor memory block, obviously, we want to deallocate the memory buffer, right? Essentially, we're going to delete that resource, the array. So we're deleting that dynamic array here. And so, but then you don't want that to be deleted, because we just want to take over that pointer. So we'll point to that location. You don't want the data array gets deleted at the end of this call, because then this data variable will be pointing to an invalid memory location if it's deallocated, and then it will be a dangling pointer, right? We don't want that. So what you do is you have to reset. You have to set the other pointer, the data, to a null pointer. So if you set this to null pointer, we know the delete is not going to do anything. So you're not deallocating. So that memory block from the other object, now we're taking that over, so that, and also it's not going to be deallocated from the other object. So that's a key statement here. If you're missing this, then it's going to be a problem. All right, so that is the this memory block class that shows you a typical use of implementing a move semantics. And so when you're constructing an object, and when you're, now let's look at the usage of this though. Actually, let's take a look at no, not this one. So we have this class defined. Let's see what impact this has, because we implement the move semantics for memory block beyond the copy semantics, which is the default semantics if you don't do anything. Now, let's say we're going to use the vector in the standard library. It's a container, and you can add as many elements to it as possible. It's so anyway, it's how the vector works. It's a container. So we're going to make one element of length 25. Then we're going to add this to vector. Now, I'm going to run this also, but let's look at this statement, what this means. So when this here, we're constructing a object memory block V1 here, right? So this is going to, and we're initializing it by invoking a constructor. Let's look at that constructor again. Let's see, bring that back. So we're invoking this constructor. Now here, you also see this explicit keyword being used again. Remember, we use this in the conversion function. We want to make that conversion explicit instead of implicit. Implicit can lead to bugs in your program. So usually, I would recommend making things explicit if you can. Now, this using in this context here, what in front of this constructor here, same thing. If you're using this in front of a constructor, it means that you have to be explicit when you're constructing this object. You have to call this constructor too. That's kind of what this means. It's explicit. You don't have to do this, but you know this is just another keyword, another usage of this keyword. So when you making a new object of memory block, capacity in the length, and here, of course, with length, we're going to allocate a new dynamic array of that length. That's what the whole memory block is meant to do. And although it's not doing any much of a useful stuff, but it's a demonstration purpose. And then we are going to push this into the vector. Now, by pushing this into vector, though, here's the thing. We'll have a function call, right? And we're passing this v1 into it. This function call, if now I'm hopping over this. Now, this v1, now remember so thinking about the L value, R value, this is very much, critical to understand this thing here. Now, v1, this expression v1 is a L value because we define a variable. It has a memory location. It's a fairly permanent memory location within the context of this method. Well, it'll go out of scope, as soon as the method returns. But it has a memory location. It's not temporary. It's, in this context, we call it permanent memory location. It's a L value. It is an L value. Now, actually push back in this standard library. This function actually takes this constant reference right here. And then later on, we're going to see it will also take, well, actually, I don't know if I have an example here, but I'm going to write an example in a second. This, in this case, is an L value. This const reference is going to take that L value. It also has another version where it takes, I believe it has another version where it takes R value. Let me actually take a look. Let's make sure. So see here, pushback. Oh, it's a very ugly to look at, but this is the standard library, the implementation. That's what the library I'm using. It has, it's hard to understand. Believe me, there's a lot of alias types and stuff like that. Okay, that's how the library is implemented. But just know that this value type would be the element type. In this case, it would be memory block that we're seeing over there. Now it does have another, and I was kind of guessing here. So a lot of the, pretty much all the standard libraries here, they actually, they have implemented the Move Semantics for most of those methods. And so in this case, it has this double ampersand. So this is taking all value reference. So if you pass something that's temporary or there's a constant, and it will move that value into the container, into the vector, instead of making a copy of it. So it's more efficient, right? So here, this is L value. What it will do here is actually making a copy. This is now remember that our copy constructor and copy assignment operator, that parameter is doing a const reference. This is, when you do this, it will basically inside of it, when you pass this into it, what the compiler will do here though, it's going to invoke the copy constructor. That copy constructor it needs to construct that the object to pass this on to pushback parameter, right? So it's going to invoke this copy constructor, right? This thing right here. And so it actually, in this case, it makes a copy. Now, just another way of saying how you might create an object, just showing you an assignment here. So this is assigning this new object into this v2. Actually, Hold on a second. V2. All right, I'm gonna change this a little bit, just actually so that you see. You know, okay, I'm gonna go with this for now, right? I'll go also make a little changes to show you what, this all value reference, and all value also showcases here too. But it's just another format of, okay, so now we're making a new object. As you actually see though, this object, when you see this expression, this is a PR value. This is a PR value. Why? It's the compiler is gonna make a temporary object here. There's at this point, looking at this expression, there's no way to refer to this, although it has a temporary location, but it will be discarded right away as soon as it assigns this to the variable v2. Okay. Now this assignment, okay, this just run this thing. It's probably a good idea to look at the results while we're talking about this. Lecture move. Okay, let's take a look at this. Now we have implemented the we have a bunch of statements to print out what's actually happening. Actually, let's look at what's happening here. So first of all, this statement 10, line number 10 is actually we're constructing a memory block of size 25, and this pushback here, as I was saying, is doing a copy. Okay, it's referring to L value using this, const reference. And this will make a copy. It's invoking a copy constructor. So as you see, this is actually exactly is going to invoke that copy constructor. Now this line here, the assignment copy assignment operator, that is just a result of invoking the copy constructor. Is reused. Remember, in that implementation of the copy constructor, where you're using the operator. So that's what this also prints out. Okay. And now we're making another object 75 with a length 75. Okay. Now here, we're also seeing another copy again. Now this copy is actually this pushback B2. Now you might wonder, I mean, we're not here, are we making a copy? We're not making a copy. This is a simple optimization that the compiler will do it. Essentially, this is a temporary. It will basically, make that variable point to this same memory location. It's not really a copy operation here. Okay, this, as you see, essentially just makes this object. There's nothing more of it. There's no copy operation here. So this is just another way to tell you that sometimes in making an assignment, but in the modern, the current standard is in the place where it can be optimized to avoid a copy, it will avoid a copy. This would be a very straightforward optimization. It will do so, actually as mandated by the language. But anyway, so there's no copy operation here. This will be essentially copied. Now, let's take a look at again. Let's see, so 25 V1. Okay, so let's look at this statement. This statement is a little interesting. We're going to insert a new element of, here we're making an object. We're making an object of size 50. Now there's another new object. Okay, we've got 25, 25 now have 50. So as you actually, the printout actually starting from here, it tells the story what's happening here actually behind the scene. Well, obviously it's not going to, this is not executing this one just yet. So in the situation where it's implementing inside the insert function, okay, it actually will move the insert operation. Essentially, you have to sort of create a new element, and then you move that into the second position of the vector. There's a movement of the elements. Okay, so this v begin +1. That means we're inserting this 50 into the location from the beginning +1. So that's basically the thinking of the beginning as the index 0 and this index 1, so it's the second location. And in the process of doing this, it's actually moving that element 25. And there's a deallocation, as you see, this deallocation because that movement. It moves that element 25 and deallocate the old temporary. And what we saw before, and is the length 0, and length 0 means you're actually deallocating that one. But that pointer, as we just saw in the implementation, that's going to be basically just stolen into that new object is moved into. The reason it's able to do the movement because we have implemented the move semantics, the move constructor and the move assignment operator. So actually the move constructor is what's going to be used here. Now, well, inside of the implementation, if it's using the assignment operator, and then you would use the assignment operator for the move semantics. Is an optimization. If you hover over this, you'll see the signature right here at the second parameter, the last one, memory block double ampersand because this is taking all value reference. Now this expression here is actually all value, So that will reference to that all value. It takes that all value and does the moves because this is a temporary object. You see, there's no more usage of this. After this statement, it'll be gone, right? Because we have not given this a name, no location, it's temporary. So it is totally okay to move this object instead of copying it, right? So that's kind of really what that also gives you. And there's a bunch of other operations that in order to make up the new list of elements in this vector. And you see there's a bunch of movements also. And it really depends on the algorithm inside the insert function, right? If you really look into the code, it's a little crazy to look at, but let's say let's not look at this thing. But it comes back to operating on these objects that we have in this vector. And this is doing the movement now inside this. And as also you'll see is doing the deallocation of the old elements as well. So it's doing a bunch of movements of the elements. It's very efficient. There's no copy happening around. Now, what happens if I do not implement? What happens if I do not implement this move semantics here? Let's just say we're going to disable this. And let's say we disable this. We don't have those things implemented. Oops. Let's see the difference here, okay? So if we don't have those things implemented, what's going to happen? You'll see everything is a copy, right? Now, starting from here, it's all copy operations because there's no move semantics that we have implemented, and everything is a copy is much less efficient than the one that we implemented with the move semantics. So especially when it's dealing with the temporaries, that it will just do the move operation instead of the. Now the previous I said I was about the okay. What if I don't use the v2? Let's say I just use this, right? Remember this constructing a new object like this. This is actually a pure value, And if you pass this into pushback, as you see, it will recognize we have an all value here. It's going to use the double ampersand, the all value reference version of that function. If that function is overloaded, as we saw, you can take a const reference. You can also take an all value reference. So in this case, we're giving it all value. We'll use the all value reference and do the move instead. So if we run this, right? So if we look at the 72, so after the 75, sorry, after this is constructed, that's what this expression will do. You are constructing a new object, 75. And then what will happen is, you see that 75 is moved. It's going to be moved into the vector. Well, actually, it's moved into, first of all, it's referred to, this takes a reference to this temporary object. And inside of it, it will be moved into the vector and then be stored there as part of this vector object V. And there's no copy here. So it's about efficiency, okay? This way your program is more efficient. Less copy, more movements, wherever it's makes sense, is necessary, okay? So that's what I wanted to cover about the move semantics. Hope that's somewhat clear. Any questions? No? Okay, good. Thank you. All right, so that's pretty much it, what I have for today, and thank you for coming. Stop the recording.